This lecture is for ELEC 1510 Logic Design. This is Lecture 11, Part 1 on Comparator Circuits, corresponding to textbook section 4.8. The operation of a comparator circuit is to basically compare two numbers, and in this scenario we're going to assume that we're comparing two 4-bit numbers, a sub 3, a sub 2, a sub 1, a sub 0, and b3, b2, b1, b0. These are not operations, these are just numbers. They could be something like 0, 0, 0, 0, and 1, 1, 1, 1. Later on we'll talk about operations where we're actually performing an AND function on two variables. So this looks like we're performing the AND function, but right now we're just writing these as 4 bits. The comparator that we're going to talk about in this video is going to have 3 outputs. The first output is going to be a 1 if the number A3, A2, A1, A0, which I'll just call A from now on, is equal to the number B, which consists of B3, B2, B1, B0. Output 2 is going to be a 1 if A3, A2, A1, A0 is greater than B3, B2, B1, B0. Output 3 is going to be a 1 if the number A is less than the number B. So we're performing 3 comparison operations: equality, greater than, and less than. So first, let's design a 1-bit equality comparator circuit. If we just look at the truth table for comparing 2 bits, so A sub I and B sub I, that could be A sub 0, B sub 0, or A sub 3, B sub 3. They're going to be equal with the 2 minterms A sub I, B sub I, or A sub I prime, B sub I prime. So if one of those 2 bits is prime and the other isn't, then they're not equal. So this is an equality comparator circuit. Now you could draw this as a typical circuit. A sub I, B sub I into an AND gate, A sub I prime and B sub I prime also into an AND gate, then an OR gate for both of those outputs, and then X sub I, which is the equality at the output. We're actually going to reformulate this equation to look a little bit different in a more convenient form for us into what's called a typical XNOR circuit. So first, if we perform a backwards factorization, we can factor out A sub I from the first term to get, in parentheses, A sub I plus A sub I prime, B sub I prime, and then in the second parentheses, B sub I plus A sub I prime, B sub I prime. In both of those expressions, something will cancel out by the absorption theorem. So first A sub I prime, and then in the second one, B sub I prime. So we're left with this expression. Now we double negate both of those parentheses terms, and we use De Morgan's theorem to rearrange the variables inside the parentheses. So now we have parentheses A sub I prime, B sub I, parentheses prime, and B sub I prime, A sub I, parentheses prime. We perform De Morgan's theorem backwards now in order to flip the operation and get rid of the primes around the parentheses. So now we have A sub I prime, B sub I, plus B sub I prime, A sub I, parentheses prime. And this is what we would call a XNOR circuit. So in order to construct the XNOR circuit, we take A sub I and B sub I, into the first AND gate, we have A sub I prime, so we're going to negate that, as well as B sub I. Into the second AND gate, we have B sub I prime and A sub I. Now these outputs from the AND gates enter a NOR gate. And so that's another way of writing the equivalent circuit. So we're going to use this circuit in constructing the entire comparator circuit later on. So this is just a little building block that we'll use later on to build the entire 4-bit comparator with the 3 outputs. All right, so let's look at how we would compare the two numbers A and B to determine if the two numbers are equal. Basically, if any of the x variables out of the equality circuits that we derived in the past slide is a 1, then the two bits a sub 3, b sub 3, or a sub 2, b sub 2, etc. are going to be equal. So if we just take the AND function of all of the x variables that come out of the equality circuits, we just AND them all together. If they're all 1, then the two numbers are completely equivalent. So that's output 1 checking for equivalence. For output 2, we would need to see if a sub 3, a sub 2, a sub 1, a sub 0 is greater than b sub 3, b sub 2, b sub 1, b sub 0. We could technically write this out with a truth table if we wanted to write out all possibilities for 8 bits. That would be a huge, huge truth table. So we're not actually going to do that. We're going to be more clever about the way that we construct this. So first, we can say if the most significant bit, or MSB, of A is a 1 and the most significant bit of B is a 0, then we know that the number A has to be greater than the number B, because the most significant bit of A being a 1 is the lowest number that could possibly be is 1000. If the most significant bit of B is a 0, then the highest number that B could be is 0111, which is lower than A still. So if this first condition is true, then A must be greater than B. What would make that true is the minterm A sub 3, B sub 3 prime. That means A sub 3, the most significant bit of A, is a 1, and B sub 3, the most significant bit of B, is a 0. So that's one possibility for saying that the number A is greater than the number B. If the most significant bit of A is equal to the most significant bit of B, we can use the equality circuit from the previous slide to tell if that's true or not. Then we look for the condition where the next most significant bit of A is a 1 and the next most significant bit of B is a 0. In this case, A sub 2 and B sub 2. So this condition would be x sub 3. That means that A sub 3 was equal to B sub 3 and A sub 2, B sub 2 prime. So this term means that A sub 3 was equal to B sub 3 and A sub 2 is a 1 where B sub 2 is a 0. So that means that the number A must be greater than the number B. So that's another possibility. This follows a regular pattern from here on out through the rest of the bits. So then let's say the most significant bit of A is equal to the most significant bit of B, and the next most significant bit of A is also equal to the next most significant bit of B. Then we looked for what I would call the next most significant bit of A, which in this number is A sub 1, being a 1, and the next most significant bit of B, that's B sub 1, being a 0. So that term would be x sub 3, x sub 2, again referring to the fact that A sub 3 is equal to B sub 3, and A sub 2 is equal to B sub 2, and A sub 1 is a 1 where B sub 1 is a 0. This would also mean that the number A is greater than the number B. And then there's an additional term for A sub 0, B sub 0, which would be x sub 3, x sub 2, x sub 1, A sub 0, B sub 0 prime. So we just take the OR function of all of these possibilities, so we put them all into an OR gate, and if any one of them is true, then A is greater than B. Output 3 is the number A being less than the number B, which basically follows the same pattern as output 2, but with the primes for A and B switched. So the first possibility is A sub 3 prime B sub 3. This means B sub 3 is a 1, A sub 3 is a 0, which means that B has to be greater than A. So that's one possibility. If the most significant bit of A is again equal to the most significant bit of B, then we look for the possibility that the next most significant bit of A is a 0, that's A sub 2, and the next most significant bit of B, B sub 2, is a 1, and that's X sub 3, A sub 2 prime, B sub 2. And then we have the next possibility, which turns out to be X sub 3, X sub 2, A sub 1 prime, B sub 1. And again, there's another term, X sub 3, X sub 2, X sub 1, A sub 0 prime, B sub 0. So ultimately, the functions for the 4-bit comparator, where the first output says that the two 4-bit numbers are equal, the second output says that number A is greater than number B, and the third output says that number B is greater than number A, or alternatively, number A is less than number B, are as follows. The first output, O sub 1, is x3, x2, x1, x0. O2 is A3, B3 prime plus x3, A2, B2 prime, and so on. Output sub 3 is A3 prime, B3 plus x3, A2 prime, B2, and so on. When we construct this as a circuit, it looks like this, and this is a diagram taken from the textbook. So this is a combinational circuit that's fairly complex and does these 3 comparison operations on 2 4-bit numbers. And you can see that we have the blocks corresponding to the equality circuits that I derived at the beginning of the video. Then we have our 3 outputs, the equality output, the greater than output, and the less than output. The rest of this circuitry performs the functions from the previous slide. This is an example of a combinational circuit where we had 2 mini input possibilities to write out all of the truth table rows, and so we had to be a little bit more clever about how we designed the circuit using sub-blocks.